This lesson, AB Calculus, APA Calculus AB, I should say, is L'Hopital's rule. And L'Hopital's rule has to do with limits and derivatives. And if that sounds familiar, I guess it should. Because when we first started learning about calculus, the very first thing that we talked about was limits, right? Okay, we talked about limits. And then we worked from limits, and we talked about something called derivatives. And as a matter of fact, the definition of a derivative involved limits, right? And so if you remember, the limit as h approaches 0 of f of a plus h minus f of a all over h was, this is formula 2, I think it was for you guys. There were two formulas when we did limits, and this became the definition of what a derivative actually was. So we talked about limits first, understood that sort of concept, and it led us to derivatives. And now we are going to be looking at, this time we're going to be looking at derivatives first, giving us an explanation or a determination on limits. So it's going to be the other way around. Now it's going to be derivatives are going to inform our calculations of limits. And that's really what L'Hopital's rule says. Let me just erase that. Okay? So again, we started off limits leading to derivatives. Now derivatives are going to lead us to determining certain limits. I need to talk to you about indeterminate forms first. We're going to be talking about this. Indeterminate forms. Okay, we're going to be talking about this kind of throughout this lesson. So if you look on page 44 in your Finney text, the indeterminate form, one of the indeterminate forms would be when you apply the limit and you get some kind of expression would yield a 0 divided by a 0. So that's an example of an indeterminate form. And when we got 0 over 0 when applying limits, then we had to manipulate, we had to adjust, we had to reorganize our expression in order to try to eliminate factors and stuff. So we're going to talk about that a little bit. But as well, if you get, infinity over infinity, positive or negative, this is also an indeterminate form, right? There's no real answer there. And where before we would say these are just undefined answers, okay? This is the situation that we're going to be using or applying L'Hopital's rule, is when we have indeterminate forms involving limits. Okay? So you inherently, from this course, you know what these are, but these are now called indeterminate forms. All right? So what have we done in the past? Let's talk about that. What have we done to find limits for indeterminate forms? An example would be this. We have limit as x approaches negative 2 of x squared plus 5x plus 6 divided by x plus 2. Okay, so here's a limit, and when you're asked to find what the limit is, okay, one of the first things that you do is you look at it and you say, okay, well, as x approaches negative 2, it would be good for me to try and plug negative 2 in for the variable to find out if the function, this rational function, if it's actually evaluated at negative 2, and if it's continuous, that might be, the limit might be that actual answer when we plug negative 2 in. So that's the first thing you would do. If you plug in negative 2, you get negative 2 squared plus 5 times negative 2 plus 6 all over negative 2 plus 2, which this is 4 minus 10 plus 6 is 0, divided by negative 2 plus 2 is 0. So here's an example where if you go ahead and plug your value in, you get 0 over 0, right? Right? Now, what did we do in the past? And I kind of mentioned a few minutes ago. What did we do to try and get around this? Because even though we get 0 over 0, meaning that, this rational function does not have a value at x equals -2, right? It's undefined, 0 over 0. We could still find a limit, right? There might be a limit that still exists. And of course there is in this one. You guys know enough about this already. But what did we do? What's that? Simplify, right? Okay, so factor, right? We want to see if we could factor things. So what we did is we wrote this limit as x approaches -2, and this was x plus 2 times x plus 3 over x plus 2. Yeah, we did that. And then we realized that, you know what? Actually, this rational function, even though this is the definition of the function, that's what the function is, really, if we simplify it, that function actually looks like x plus 3. Okay? That's what it actually looks like. It looks like the line x plus 3 with this small, side note, right, that it's undefined at x equals -2. Right? So there's a gap, right? And we talked about that, a gap. So if you were to graph this right here, you would have a function that looks exactly like this line, except there would be a tiny bit of it missing. And that's where x is -2. But now what we could do is we could say, all right, let's plug -2 in for x and see what we get. And here's 1. So we would guess that the limit is 1. And we could graph that and we could see. So let's graph it. So here's the graph. If we graph that, see, it looks like this line, and that looks like the line, y equals x plus 3. So it has a slope of 1, it has an intercept of plus 3, but at -2, I don't know, I'm going to zoom in here as much as we can, and yeah, I don't know if anything's going to show up here, because I'm zooming in pretty good. But remember, a point on a graph, right? A single, oh, what do we got? We got something happening here. Nice. Whoa! Look at that! That's mind-blowing. Look at. Is that amazing? I've actually never done this before. Look at this. The graph, as it gets close to x equals -2, look at it. It starts going crazy. I love it. And then look at, right at x equals -2, we have an asymptote. Look at, this is amazing. This is like a glimpse. This is like quantum physics or something. Look at the electron. It's bugging out, man. Look at that. It just does not know what to do. That's amazing. I love it. Okay, so, wow, I was not expecting that. I am just so pumped. This is way better than just a gap, right? It's like, look at, this is like a total freak out. I love it. I don't even know what the scale is here. What's the scale? Like, this is like a millionth or something? That is a thing of beauty. I'm sorry. I'm sorry. That's amazing. Okay. The bottom line is we have an issue right here at x equals -2, right? Because look at, it would be undefined. But if we zoom back, oops, that's in. If we zoom back out, that's so awesome. If we zoom back out, the graph really just looks like x plus 3. See that? Okay, we get that, right? So we know there's a limit there. From the left side, the limit approaches what? 1, because this is 1. From the right side, the limit approaches 1. Okay. Now, besides the fact that this is just stinking amazing right here, this is unbelievable, I love that. Look at that. Okay, let's get back to reality though. All right, so what do we do now? What is L'Hopital's rule all about? Well, we said that derivatives have some kind of key here. So what I'm going to show you will also blow your mind, okay? Something that's not quite as exciting as what happens at a gap, discontinuity on Desmos, but this is kind of cool. Okay, let's think. Now this is in red now. What is the derivative of this right here? The derivative. What's the derivative? 2x plus 5, right? You guys know that. That's awesome. What's the derivative of this? 1. When you put x equals -2 into this expression now, what do you get? You get -4 plus 5 over 1, which is 1. Now that is interesting. That is very interesting that when I take the derivative of the top and divide it by the derivative of the bottom, I get the same number as the limit. That's interesting. And I didn't have to go through the whole factoring, dividing, factoring, got the same answer, okay? I think what we should do is we should try another example. Okay, here's another example. The limit as x approaches 0 of sine of x over x. Right now, you know you're going to have some kind of issue because if you put 0 right there, you're dividing by 0. All of a sudden, you've got an issue. I don't know if it's 0 divided by 0, but if you put 0 in for sine of x equals 0, sine of 0 is also 0. So if we just go ahead and plug 0 in, we get 0 over 0, right? But if we think about how we dealt with this in chapter 2, I would try and factor the top and factor the bottom and divide out a common factor, but everyone knows that it is just completely ridiculous to think of doing this. We couldn't do that, right? That is a sin right there. That's what that is. Right? You can't do that, okay? It's bad. So we can't factor sine of x. Well, could we factor it? Could we write it as something else? Yes. We could write x squared as something else as well, I guess. But why would we? We're not going to be able to get a common factor, right? So what do? Well, let's try this whole derivative thing. All right? So let's take the same limit as x approaches 0, but let's take the derivative of the top. What's the derivative of sine? Do you remember? Cos of x. That's true. What's the derivative of x? 1. Okay, so just for kicks, right? Took the derivative d dx of the top and d dx of the bottom. Just for kicks. Now, if I plug 0 in for x, it's only in one spot there now, so I'm not going to have 0 on the bottom. That's awesome. What's cos of 0? 1. Okay. Well, that's not 0 over 0, is it? The question is, what is the actual limit? Could we determine that graphically to see if this 1 turns out to be anything? Well, the answer is, of course we could graph that. I'm just wondering if I have this saved. Oh, look at this. I actually have one. I love this. It's so good. Okay, that's my favorite part of the day. I know it's Valentine's Day today, and I should be thinking about my wife, but I'm thinking about that graph right now. That's like the most exciting part of my day. Okay. Okay, that's not the one I want. Give me a second. Yeah, I know you're thinking, I do not want to become a math teacher. Because on Valentine's Day, they think about graphs. That's terrible. Yeah, it is terrible, actually. Don't. Desmos disturbed me. Okay, brackets, sine x. Thank you. There's sine x. Look at that. But we're going to divide this by what? X. Dun, dun, dun. There's the graph right there. And as x approaches 0, what's the limit? I wonder what happens at 1. Or at 0, I mean. Let's see. We're zooming. We're zooming. We're zooming. Let's see if there's something at the bottom of this tunnel. Come on. Come on. Do you feel like you're like running a race or something? Or you're like running away from something? Oh, that's as far as it'll let me zoom. Suck. Are you guys as disappointed as me? Probably not, eh? That's too bad. I know. I am super disappointed. Okay, zooming out. We're zooming out. We're zooming out. We're zooming out. This is getting really exciting for you. I know. We're zooming out. So the limit here, anyways. I know we didn't have like a real fancy, something happening there. But look at the limit is 1. So let's go out into the atmosphere here and see what it looks like from high above the Earth. Look at that. Nothing. Okay? Yes. And the wheel on my mouse is going round and round, and it's getting worn out. Okay. So, that's good news, isn't it? Now, you guys do this one. You guys do this one. Go ahead. No, I dare you. Do this one. Find out what the limit is as x approaches 0. Okay? Without graphing it, and I'll show you what the graph looks like. But as x approaches 0, find out what the limit is for this graph. I'll give you a second to do that. Is that what you got? Scoot, scoot. You got 2? Okay. So here's all the work shown. Just go over this real quickly. First of all, I plugged in 0 into my original equation, and of course you get 0 over 0. Indeterminate form. So if we're trying to find a limit, obviously we can't factor anything out and divide like we could before. So let's try L'Hopital's rule. Take the derivative of sine of 4x. Did you get the derivative to be 4 cos 4x, guys? You remember a chain rule? Okay, good. Very important. Okay, so that 4 over 2 is a constant. When we're talking about limits and x's, that can come out. So there it is. Plug in 0, what do you get? Now we get cos of 0 is actually 1. So we get 1 over 1. Right? This right here is 1 times 2, 2. Okay, so L'Hopital's rule says that we should get a limit as x approaches 0 for this particular function, sine 4x or sine 2x. We should get approaching 2. So let's just see. And 3, 2, 1. Was it frozen the whole time?
Yeah.
Okay. There we go. Look it. Check it out. I'm not going to zoom in forever here. But look it. What was it? That's 0. Okay? X equals 0. Limit is 2. So what am I telling you here? What I'm telling you here is that L'Hopital's rule says that we can find limits of indeterminate forms. Okay? When we have an indeterminate form, we can still find the limit. Now, I am going to give you one more example, and I'm going to let you take a look at something else that's kind of cool. Not as cool as that gap discontinuity, but still pretty cool. Okay. Okay, so here's an example of a question we're going to do. And if we plugged in x equals 0 here into this equation, what would we get? Well, we'd get sine of 0 is 0 minus 0 divided by 0 minus 0. So we would get 0 over 0. Does that make sense? All right, so what do we think of? Especially when we can't just factor and divide out factors. What do we think of? What rule do we think of? The one we're learning today that I've said. Not lay hospital. No, I'm sorry. It's not lay hospital. It's l'hôpital. It's like, thank you, l'hôpital. Okay, not lay hospital. This guy is not in the hospital. Okay, so let's try that one. Let's take the derivative of the top and the derivative of the bottom. Okay, let's see. Can you see that on the screen? I'm going to take the derivative of each of these and see what it gives us. Okay, so what's the derivative of 2 sine of x? Of course, I'm going to rewrite my limit like I should. What's the derivative of 2 sine of x? Well, the derivative of sine is cos, right? So does that make sense? That's 2 cos x. Chain rule says I multiply by 1. Leave that 2 out there. I'm good. So what's the derivative of sine of 2x? Derivative of sine is cos. So we've got cos 2x, and then chain rule says I multiply by 2. Okay, very good. On the bottom, what's the derivative of x? 1. What's the derivative of negative sine x? That would be negative cos x. True? The derivative of sine is cos. All right. So if we do that, now, what does that mean? That means we just plug in 0, and then life is rosy, right? So let's just do it. So we've got 2 cos, cos 0, minus 2 cos 2 times 0, all over 1 minus cos 0. Okay, awesome. This is looking really, really good. So cos of 0 is 1, so that's 2 times 1. And cos of 2, that's still cos, that's 2 times 1. Okay, awesome. Then we have 1 minus, 1. Ouch. Whoa, what? We've got 2 minus 2 over 1 minus 1. Okay, so we applied L'Hopital's rule, and we still get 0 over 0. What do we do? What do we do? Does that mean L'Hopital's rule doesn't apply? Do we have to do something different? Any suggestions? Okay, think about it this way, all right? Think about it this way. This is great. You're going to love this, okay? What if, just what if, my original function was this? And I plugged 0 in for x, and I got 0 over 0. What would you do? You would apply what rule? What rule are we learning about? No, not lay hospital. You would apply L'Hopital's rule, right? Right? So, who's to say we couldn't try it again, guys? Listen, it doesn't matter if you get 0 over 0 after taking the derivative. You have to realize that any function, right? I mean, any function, including this one, what is an original function? What is that? This could be the derivative of another function, right? If we integrate this, which wouldn't be a lot of fun, but we could, then would that be the original function? Or could we integrate that function again? You see what I'm saying? So don't get discouraged if you apply L'Hopital's rule and you get 0 over 0. Just do it again. That's what we're going to do. That was very liberating to me when I found out that, you know what? If you get 0 over 0 again, don't cry and moan. You just keep going. Home. Okay, so what's the derivative of 2 cos x? What's that derivative? The derivative of cos is, come on, negative sine, thank you. So negative 2 sine x. What's the derivative of cos? Well, we just said it was negative sine. So we've got negative 2 sine 2x. Chain rule says I got to multiply it by 2. So we have negative, negative, that's positive. 4 sine 2x. Okay, does that make sense? Did I do that right? So it's negative sine, negative, negative, sine 2x times 2, 4. Okay, I think that's right. So what's the derivative of 1? 0. What's the derivative of negative cos? Well, the derivative of cos would be negative sine, so this should be plus sine x. Okay, how is that? Does that look right? Does that look okay? All right, this is awesome. Now we're going to get somewhere, right? So this is negative 2 sine of 0 plus 4 sine of 0, 0 plus... Ah, doggone it! Look it! Look it! 0 plus 0! So now is the time where we cry and moan and feel bad for ourselves, right? Or...
Again!
Again! Thank you! Let's do it again. Why not? Because I don't know, maybe this was the original function right here. Maybe that was it. And then you wouldn't feel bad, would you? No. You'd just go ahead and apply L'Hopital's rule. So let's go ahead and apply L'Hopital's rule. I think there is an end coming. But this is a great example of perseverance. You have to persevere. All right. What's the derivative of negative 2 sine x? Negative 2 cos x. You guys are getting faster now. What's the derivative of 4 sine 2x? Oh, I love it. 8 cos 2x. The derivative of 0 is, okay, that's gone. Derivative of sine is cos x. Da, da, da. The heavens are opening here because look at cos of 0 is actually not 0. Beauty. Okay, so if we apply, it includes 0 here, okay, plug it in, you get negative 2 cos of 0 plus 8 cos of 2 times 0 all over cos of 0. And cos of 0s are 1, right? So this is looking real good. 8 times 1, this is 1. So what does this look like? Negative 2 plus 8 is 6 over 1, or 6. Do-do-do. Okay, so we have a number that appears to be what the limit is. Now, if we've done our derivatives correctly, and if L'Hopital's rule is legitimate, then we might say, hey, the limit here, as x approaches 0, is 6. So let's just pause and graph the original function. And so here we have, we're going to graph it, and the big reveal. Yes! Right there! Look at it in its full glorious form. Look at that, it's approaching 6. Okay, so what happens if I zoom in? Look at it! Look at it! Ah! That's awesome! That is so awesome. Look at that. That is called bugging out right there. It's like, ah! But this is a great, hey Sam, look at this one. This is good for you too. Look at, okay? All right, so look at, if we approach, okay, we're approaching x equals 0 from the left, it really gets a little bit wonky here, okay? So at 0, we are in trouble. But as we approach 0, and this is a great view of it, as we approach 0, closer and closer and closer, it appears to be approaching this y value of 6. You see that? And from the right side, if we're approaching x equals 0, we are approaching this y value of y equals 6. Because look at, if I put this, that is so beautiful. 0.0000094, comma 6. Look at this. Oh, unbelievable. Okay, so what's going to happen here as we get closer and closer? I think my computer's going to explode, but look at that. Still 6, still 6, still 6, and it's like, what are you doing to me? Off the radar almost. Look at this. Oh, look at it. It's taking time to think. It vanished into space. It's like the Philadelphia experiment in Regina. What? It's like the Regina experiment. Look at it. That is amazing. But you see how the y value is 6? Okay, that totally made my day. All right, so let's zoom back out. Look at, hey, look at all these points. Look at all those points today. That's awesome. Okay. Any questions? What happened? Oh, vanished. Look at. It's not good for us to apply L'Hopital's rule too many times. Look at this. It's like a secret message. Okay. Yeah, that's right. That's right. I used to write in black, but I can't get a black screen anymore. It's all only white. It's really sad. Any questions? No? Good. That's L'Hopital's rule. That's already, long enough for you guys. So here we go. L'Hopital's rule. Derivatives give us a clue to limit. So just take the derivative of the top and derivative of the bottom and take the limit as x approaches the number in question, x approaches a, and apply that limit. So just basically just plug it in. And you could do one-sided limits as well. And one-sided limit might take you to negative infinity. The other sided limit might take you to positive infinity. You never know. But at least you have some kind of indication as a limit. So L'Hopital's rule. There you go.